Okay, picking up where we left off on page 365, we're talking about data normalization. So let me just hit some of the highlights, and I'll be very specific about what portions of this I'm expecting you to take in, and what portions are going to be on the test. So normalization is a process of creating tables designed by assigning specific fields or attributes to a table or a series of tables. Essentially, normalization is breaking things apart. Okay, so you end up with like one giant Excel spreadsheet with tons and tons of information, and you end up with 4 or 5 tables that represents the same thing. Normalization involves applying a set of rules that help you identify problem areas. The classic example is what we just talked about. Let's say that 2 of you in your household are getting a magazine subscription. So you could have you and your address in one table. That perfectly makes sense. And then your spouse orders a subscription, so they have a different name and the same address. And so your spouse calls up and says, hey, we're moving. Can you, we're going to a different, we moved to a different city because you change us. And so they're going to change that one row. And so your spouse, the other spouse, is going to end up getting the magazine sent to the old address, and what other one's going to be sent to the new address. How much better would it have been if they said, here are 2 people, and here is the single table with this address in it. And so if I change it one time, it happens everywhere. That's the essence of data normalization. And it talks about 4 particular stages. You have the unordered list, some sort of like an Excel spreadsheet that's not in any database whatsoever. And then you go to the first normal form, and then the second normal form, and third normal form. I'm not going to ask you the specifics about how to transition between those forms. I may ask you a question about, what does first normal form stand for, those kinds of things. But what I'm really interested in is, why the heck would I want to do this anyway? And so there are some pretty good reasons why you want to do that. I just gave you kind of a scenario. So I'm going to pop over and look at this cool little diagram here. This is just something I found on the web. So here is a customer. So you have a customer and a customer ID and a date of birth, and then you have their address. And they said, there could be a scenario where I have the customer's address in the billing department. I might have the customer's address in the shipping department. I might have the customer's address, someplace else in user feedback, or I could have the customer's address in multiple locations. And that's bad, because when they call in to change their address, wow. So they recommend that you create a separate table with the address. And then now you have the customer table that's been stripped of its address information, and all it does is have some sort of an email ID that points back to this other table. So here are the advantages. The advantages are removing transitive, don't worry about the word transitive dependencies. That's just a term they use for third normal form. So don't worry about that. The advantages are mainly twofold. First, the amount of data duplication is reduced. So I don't have the address in 5 different locations. Okay? And therefore your database becomes physically smaller. I like that. The second is data integrity. We mentioned data integrity before. Where duplicate data changes, there's a big risk of updating only some of the data, especially if it's spread out in a number of places in the database. For example, if the address and zip code were stored in 3 or 4 different tables, and they changed the zip code, that change to the zip code would have to ripple through all 4 tables, and there is a likelihood that it will not occur. However, if you only had it in one place, then you make that one change and there's no possibility of them not getting it right. So, the purpose for normalization is help you to create a database that's practically foolproof, that does not have any duplicate data at all. That's kind of the point. And the point of duplicate data is I could make a change in one location and forget to make a change in the other. And it happens. I mean, I still get subscriptions with two different spellings of my name. That could not possibly happen if they built their thing correctly. So that's what third normal form is all about. So there's only 3 normal forms? Well, no, there's actually quite a few more. They go on and on and on and on. But again, this is not a database theory course. This course is about, system analysis and design. So, yes, there's more to learn here, but not in this course. So, first normal form, I basically want you to know a little bit about it. Here's another example of first normal form. Let's say, for example, I had an Excel spreadsheet that was unstructured, and there was a field in there for a telephone number. And so somebody just put in, 555-1234-5678. And then the next row, the guy put in 2 phone numbers. He put in one for his home and one for his cell. Like put a comma or something and put 2. Now, when it comes time for you to analyze the data and say, I want to pull everything up by area code, well, it's not going to work because you've got 2 different ones in one field. So that's bad. That's kind of a violation of first normal form. Okay. Second normal form talks about this thing called functional dependency. And the key to functional dependency is that if you give me one piece of information, I can give you the rest. In other words, given the guy's customer ID, I can provide you with his name, his date of birth, and his zip code, as an example. So given something, I can give you something else. So functional dependency is what second normal form. Third normal form is transitive dependencies, which means I've got a table that I think is functionally complete. However, there are things in here that do not refer. In other words, this guy's customer ID is really related to him, but not his address. So there is a functional dependency, where you've determined that something else could control the address. Okay, so those are the definitions of first, second, and third form. All right, I'm going to skip over a bunch of this stuff. And let's go look at an example on page 377. So on page 377, they have this thing. Now this is a relationship diagram that is generated automatically. So for example, Microsoft Access can produce this. And this kind of looks like a Microsoft Access one, but I can't tell. It could be SQL Server. But it's definitely a diagram produced by some piece of software. Now, if you look at this, you might think, geez, that looks like a whole spider web of stuff there. I mean, you got labor codes and parts and customers and all this weird stuff. And if you look at it long enough, you can kind of sort of see how things start to make sense. First of all, let's look at the cardinality. For every customer, a customer could have more than one service call, right? A customer could have more than one service call. Yeah. A technician could have more than one service call. That makes sense, right? And that a service call could have some labor, more than one labor, or more than one parts. That makes sense. And that parts could have, for every parts, there are one description, one price code for those parts. Likewise for labor code. If I put a labor code in there, it's probably a list of labor codes. So for there is a labor code that so this thing kind of sort of makes sense. So there's another way of looking at it on the next page. This is the exact same thing, slightly different. Where they're talking about, customer numbers come over here and call numbers go over there. And take a minute to kind of look through this, because this is pretty doggone cool. This is what the real world data normalization looks like. Now this looks complex, and quite frankly, it is. But I will tell you, in my experience, if you do not design the database correctly the first time, you will pay for it. I promise you. You've got to learn how to do this. And I can walk into an organization and look at their database and go, I bet you're having problems with this, this, and this. They go, wow, how did you know? It's like, because I can tell. Your database is not designed for that. It's going to mess up. Okay, so these real-world examples are probably a little better than looking at all those goofy charts and all the pages before. Alrighty. So on page 379, they're talking about kind of the upper level thinking about what kind of questions you might get if you're a database administrator or when you're a data knowledge worker. And using a relationship between all these tables, you can make sense of all this. They're going to ask you questions like, did a customer receive service on this particular date? Well, yeah, because you built it correctly, you can actually go to the service call where the date is and find out if someone had done something on that date. Yay! The technician, Marky Johnson, put more than 6 hours of labor on any service call. That's pretty cool. Well, let's see. Where would I go to find that? So you need, if you're asked those questions, you might go, well, how about the labor service detail? Okay, yeah, that's the one. Were any parts used on service calls in Washington? Ooh, okay. I need to get the address where Washington is. I need to get the service call, and then I need to be able to find the parts. And so 3 different tables involved to be able to answer those questions. These are real life questions that could happen. Okay. So let's go on down to page 381 where they're talking about using codes. Now, they go on for a couple of pages here, and I'm going to hit the highlights because, quite frankly, these concepts are not at all difficult to understand. So I don't know why they went pages and pages and pages on this. It's pretty straightforward. And that is, I could, instead of typing out something every single time, I could have certain codes that make it a little easier. You know what I'm talking about. Like when you go to the airport and they want to put a baggage tag on there. They use a 3-letter code for the airports, right? So they don't have to type it all out. They can just have a 3-letter code. And they use those codes so often that they basically have them memorized. They might have to look up 1 or 2, but essentially they know. Do we know what the codes are? Maybe, maybe not. Is it relevant that we know what the codes are? Not at all, because we don't have to deal with them. Okay, so they talk about codes can reduce data input errors because I don't have to type in Dallas Fort Worth. I can just type DFW. So they're easy to remember sometimes, and the code itself could provide some information. It could provide some context. And then they go into the types of codes, and again, I'm going to go through this a little quicker than what they have. They talk about block sequences. Okay, we use block sequences in the how courses are put together. A 200 level course and a 300 level course and a 400 level course. Yeah, block numbers. That makes sense. Alphabetic code, such as like the 3-letter abbreviations for airports. Significant digit codes, derivation codes, cipher codes, action codes. Anyway, you guys know what we're talking about here. The choice to use codes or not is probably a heck of a lot more important than these examples. And they talk about, if I'm designing a code, what should I consider? Well, I should consider keeping it very concise, allowing for expansion so that, if I run out of 3-letter codes, I might have to go to 4. So let's go ahead and make it 4-letter codes to begin with, that kind of stuff. Keep the codes stable. Don't change them. Jeez, that would be a mess. Keep them all unique. Make them sortable if that's relevant. Some sort of a simple structure, design that so it's not going to be confusing. Make them meaningful as possible if you can, and use a code for one particular purpose. Don't use an action code, for example, in multiple locations, even though it might mean the same. Make it context specific, and then of course everything is consistent. Okay, we're running out of time, so we'll pick this up again in just a few.